Hello, calculus fans. Okay, so we're going to talk about higher derivatives now. So we start with a function that's differentiable, and that means that we can create a new function, f prime of x. Now, if we're lucky, it might be the case that this new function has a derivative of its own, and we're going to call that f prime prime. And we'll call that f double prime. So that's this thing here, and that's if we were to take a derivative twice. So this new function is called the second derivative of f, since it's the derivative of the derivative. Now, if we use the Leibniz notation instead of the Lagrange notation, we can write the second derivative of y equals f of x as the derivative of dy by dx, and then the way we'll write that is it looked like d squared y over dx squared. Okay, so let's suppose we have f of x equals 4x cubed minus 5x. I'd like to find a formula for f double prime of x. Now we've actually already computed the first derivative. We did that in an earlier video. We computed that f prime is equal to 12x squared minus 5. So we'll use the definition of the derivative again to compute a second derivative. So if we want to compute the second derivative, then this is going to be equal to the limit of f prime of x plus h minus f prime of x all over h. If we hadn't previously computed this f prime, we'd have to do an initial limit calculation to compute that. But we've done it already, so now we're essentially doing the second limit computation. So we'll plug everything in now into the first derivative. So notice that we're plugging all of these things into this function here. Okay, so we've played this kind of game before. We just have to do a little bit of algebraic simplification. So I don't really want to dwell on the details. Multiply everything out, do some canceling, look to try to cancel the h in the bottom. We've done this now quite a few times. I think everybody's starting to get used to it. Once we do some canceling in the top, we get this, right? You can see that the 12x squareds cancel, the 5's cancel, and we're just left with 24xh plus 12h squared. Remember what our goal is, to try to cancel out the h that's in the bottom. So if we factor out the h, now we can go ahead and cancel out the h that's in the bottom, the thing that we've been trying to do. Once we cancel, then we get a limit of 24x plus 12h. And at this point, we can go ahead and plug in h equals 0. The direct substitution property applies. So we get 24x for our final answer. Now we should talk a little bit about interpretations of the second derivative. So we would say that they're a rate of change of a rate of change. And physically, the most common use of second derivatives is that they can represent the acceleration of a moving object. And we'll talk a little bit more about that later on. Okay, that's all for now.